Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today, flip equivalent binary trees. In this problem, we are given the root of two binary trees, root 1 and root 2, and we should return true if two trees are flip equivalent or false otherwise. For a binary tree T, we can define a flip operation as follows. Choose any node and swap the left and right subtrees. A binary tree X is a flip equivalent to a binary tree Y if and only if we can make tree X equal to tree Y after some number of flip operations. Then in example 1, for the given two trees root 1 and root 2, we return true because both of the trees are flip equivalent, as we can make flips at node 1, 3 and 5. As you can see, when we flip at node 1, we swap left and right subtrees. So now the nodes 2 and 3 match. Then we flip at node 3. So instead of 6 being the left child, now it is a right child in root 2. So that also matches. And finally, after the flip at node 5, 8 becomes a left child and 7 becomes a right child. So they also match. And because we can match both the trees after 3 flips, they are flip equivalent. Now when we are checking if both the trees are flip equivalent or not, the root values of both the trees should be same. Because root cannot be flipped, flip operations can only affect the left and right subtrees. So here we can see that the root value 1 matches in both the trees. So now let's go to its children. Let's go to the left subtree first. And now the simplest case could have been when left subtrees of both the trees are exactly same. In that case, we can return true for this path because the left subtrees are flip equivalent by default. However, in this case, subtrees are different. That is, we have node value 2 in tree 1 and node value 3 in tree 2. So that means we should perform a flip. And when we are performing the flip, we don't have to make the actual modification. What we can do is, we can actually compare the left subtree of tree 1 with the right subtree of tree 2. And here we can see that left subtree of tree 1 is 2 and right subtree of tree 2 is also 2. So that means they match. But we have to match the left subtree. So now we need to recursively check for the children of these nodes as well. So we continue down with the recursion. And here we can see that left child of node 2 in tree 1 is 4. And same is the case in tree 2 as well. So they match. We don't require any flip. And as node 4 does not have any children, we are done with this path. So now we go to the right child of node 2. And right child of node 2 in tree 1 and tree 2 is 5. So we don't need any flips again. Now we go to the children of node 5. Now left child of node 5 in tree 1 is 7, but it is 8 in tree 2. So they don't match. And so we can perform a flip. That is, we can compare left child of node 5 in tree 1 with right child in tree 2. And now they match. So the flip actually worked. And now node 7 does not have any children. So we go to the right child of node 5, that is 8, and compare it with the left child of node 5 in tree 2. And both of them match. So that means whole of this left subtree is actually flip equivalent with right subtree of tree 2. And now we will compare the right subtree in tree 1 with left subtree in tree 2. And we can see that node 3 actually matches in both the trees. So now we go down to its children. And then we see left child of node 3 is 6 in tree 1, but it is null in tree 2. So maybe we can make a flip and compare left child of node 3 in tree 1 with right child of node 3 in tree 2 and see if they match. And luckily here they matched. And now because 6 don't have any children, we are done with this path as well. And now for node 3, it does not have any right child. So we are also done with node 3 as well. And because we can make each label match by performing these flips, both the trees are flip equivalent. So now to summarize, we start by comparing the root nodes of both the trees. If they don't match, that is, if one of them is null and another one is not, or if both of them are non-null but their values don't match, then they are not flip equivalent. But if the root node values match, then we can actually check if the left subtree and the right subtree are flip equivalent or not. And here we will have two cases. We may not require flipping. Left subtree in tree 1 matches with the left subtree in tree 2 and right subtree in tree 1 matches right subtree in tree 2. Or we may require a flip. That is, left subtree in tree 1 matches with the right subtree in tree 2 and right subtree in tree 1 matches left subtree in tree 2. And if at any point they don't match with or without flipping, then the trees are not flip equivalent, otherwise they are. So that's how the logic will work. Now let's jump into the code part. First, let's write our base case, and that will be if both the nodes root 1 and root 2 are null, then we should return true, because that means they are equal. But if only one of them is null or their values are different, that means they are not flip equivalent. So we should return false. And if the value also matches, now we have two cases. First is the case of no flip, where the left subtree of the first tree is flip equivalent to left subtree of the second tree, and the right subtree of the first tree is flip equivalent to the right subtree of the second tree. Or the case where we have to flip, where the left subtree of the first tree is flip equivalent to the right subtree of the second tree, and the right subtree of the first tree is flip equivalent to the left subtree of the second tree. So if either of the unflipped case or the flipped case holds, the trees are flip equivalent, otherwise they are not, and hence we return it as our answer. So now let's run this code. Let's submit this code. Cool. In terms of time complexity, it will be O of n, where n is the number of nodes in the smaller tree. And when we look at this recursion logic, it may look like that we are taking some kind of a decision. So it should be like 2 to the power of n. But actually that is not the case. And the reason for this is, if we go to the constraints, it is given that each tree will have a unique node values in the range 0 to 99. So as soon as we find out that the tree is not flip equivalent, we return back and terminate the recursive call immediately. So in the worst case, which is that the two trees are flip equivalent, the extent of the recursion will be covering the smaller tree, and hence the time complexity here is O of n. And in terms of space complexity, it will be O of h, where h is the height of the shorter tree, primarily coming from the recursion stack. And one final point on this code, we can actually make this code concise, but that may affect the readability. But if you still prefer that code, that is also available in the code link, linked in the description below. Please check it out. So that's it. So I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. If you have any questions or comments, please write them in the comment box. Thanks for watching. See you next time.